Recording, and homework one was due on Wednesday, and I know all of you have submitted the homework. I'll try to get the grading done by the weekend. So we'll very quickly
Jen White is on here too.
of the homework, and then we'll start discussing about feedback. So of course, the first three problems, I mean the solutions, I'll post them right after this class today. However, I'm solving them in a very the way that we discussed in the class using voltage divisions, current divisions, and so on. I guess the first problem was pretty straightforward. Again, you have to work your way backwards from the output side toward the input and find out what are the effective impedances that you see looking into the network. Let's see. Looking into the network, for example, at this point, what do you see? You see this 30 kilo ohm and 10 kilo ohm, which will give you 40 effectively. And then what do you see looking here? Then you see a 40 kilo ohm, and then in parallel, you see another 40 kilo ohm, and so on. So in that way, you can just work your way backwards toward the source. And when you have a very simple voltage division near the source, you just work your way forward eventually to find out what is the voltage drop across the final load resistance. So again, it's a very simple voltage division problem, something that is very similar to what is shown and solved in class. Eventually, you should come up with this particular number as your voltage gain. Note that your voltage gain is less than 1, which really means you have a loss. And that is expected because this is a passive network. There is no amplifier here. There's no element that can increase the voltages, right? So you'll always get a voltage loss if this is a passive resistive or capacitive network, for example. And in this case, it's a passive resistive network. You have a gain of 1/8, which means you have a loss. Anything less than 1 is a loss. The second problem was again very similar to that. It's again a voltage division problem. You have your VS source and VO at the output. Again, using a very similar way of calculation, you get to, if you have gotten 1/4 or something very close to that, your answer is correct. The third problem was a current division problem, again, similar to the one that was shown in class. The method is exactly the similar. Start from the load, work your way backwards, try to find out a current division which looks very simple, like that, what is being shown here at the bottom. That if you write down the equivalent resistances, eventually you come up with a very simple current division network. And from that point onwards, work your way forward until when you find what is your IO, the load, the current that is flowing through the load. Problem number 4 and 5 were related to amplifiers. Again, we discussed a few of these similar problems in the class. You'll see a voltage division at the input side because of the finite input impedance of the op-amp. So there would be a voltage division here. And because of the non-zero output impedance of the op-amp, there would be a voltage division here. So you'll have those two ratios, and you have a gain of 100 in the middle, which is this given by this dependent voltage source. So your overall gain would be this voltage division multiplied with the gain, the ideal gain, multiplied with the voltage division at the output side. And again, as you see that you come up with, if you have come up with something close to 75, it should be fine. And of course, there are some approximations made here. You may want to make those approximations. Why? Because, again, think about it, that if you choose a 10 kilo ohm resistance in the lab, it may never be exactly 10 kilo ohm. It could be 10.001, it could be 10.2, it could be 9.9, but it may never be exactly equal to 10 kilo ohm. So does it really matter if you are trying to find out the gain of the whole system, that whether you have approximated a little bit and then instead of writing maybe 74.3, you are coming up with a gain of 75, or instead of 75.1, you're coming up with a gain of 75. And that's perfectly fine because that's how electronic systems work. Right? There's no point going to third decimal place kind of accuracy because your components will not be that accurate. Even though in a math problem, things may look that accurate, but in a real life, it will never be. And that's what I mean by design-oriented analysis, that as long as you do the correct approximations, assumptions, and come up with the solutions in a fast way. So for example, let's just think about at the output. So for example, RL is 10 kilo ohm. The RO is only 100 ohms. So the voltage division ratio you have is 10 kilo ohm divided by 10 kilo ohm plus 100 ohm. It doesn't really make sense to calculate what that value really is. It will be very close to 1. It could be 0.999 something, or maybe 0.98 something, right? So it's almost as good as a ratio of 1. So it doesn't make sense to spend a lot of time on figuring out what that exact ratio is As if it is very close to 1, write it down as 1, because anyway in your components, you may not find anything that is exactly equal to 100 ohms. You may not find anything that is exactly equal to 10 kilo ohms. So it doesn't make sense to try for that degree of accuracy when you're solving the math problem, because in real life, it will not be as accurate. So come up with those kind of assumptions and approximations in a fast way so that you can solve the problems quickly. That's what companies like TI or Analog Devices will look for when they come for an interview. So try to solve them fast, make those clear logical assumptions, and make sure those assumptions make sense. And that is the way to come up with the solutions in a fast way. I mean, of course, you'll get the full grade if you are writing the answer as 74.3 or something like that. But what I'm really looking for is whether you are really able to make those correct approximations and assumptions and trying to make your life simpler in a logical way. All right, so that's our problem 4. Problem 5 was very similar. It's just that it's a dual of problem 4 in terms of the way the amplifier has been modeled. Instead of modeling the amplifier as a voltage controlled voltage source, in this case, we're modeling it as a voltage controlled current source. You have to be careful about the direction of the current. Remember that the way this has been modeled, the direction of the current is here. You could have done it the other way as well. Just depends on how you model it. Now, if the current direction is this, then of course the voltage that gets developed at that point would be negative because current is coming out of this node and basically going to ground. Right? So just make sure that you have taken care of the sign in your calculation. But otherwise, the calculation should be very similar. So you have a voltage division at the input side. And then for finding out the output voltage, what you can do is that you already know what is the current that is flowing in this node. What is the current that is flowing here? Now, looking on this side, what is the resistance that you see? You see a 200 kilo ohm in parallel with another 200 kilo ohm. So basically, you have 100 kilo ohm because of the parallel combination of those two. So you have your current, Gm times V in, multiplied with that effective resistance. That would give you voltage, Ohm's law. Current multiplied with resistance gives you voltage. So you can write down in the form of that output voltage that you see, which would be this minus Gm times V in times R equivalent, and R equivalent is 100 kilo ohm because these are two 200 kilo ohm resistances in parallel. And from there, you can just directly calculate what would be the ratio, VO over Vs. Now, I saw in the chat that some of you asked that, okay, the value of Vs or Vin is not given. So how do I find out the output voltage? So remember, in this case, you are asked to find out the gain, and the gain is a ratio of output to input. So you don't need to know the value at the input. As long as you find out the ratio from the output to the input, that's what is asked for in the question, right? So your Vs could be 1 millivolt, it could be 10 millivolt, it could be 5 millivolt, it could be anything. It's just that the ratio or the gain of this system will determine what your VO will be. Okay. Any questions related to the homework? Yes.
Why is GM negative?
No, sorry, GM is not negative. See, depending on, because this current is in this direction, if you're trying to find out the voltage, what is the voltage at this node? That is minus GM times R equivalent, right? That's why the negative, the minus term comes in. Question? Exactly. So you'll see that this is exactly the model of a MOSFET, right? So if you, when you study MOSFET, you'll see that this is exactly the model of the MOSFET, where you have a voltage controlled current source, and then that current multiplied with the effective output impedance gives you the output voltage. Now, what is interesting here is that, see, the gain, of course, there is a term over here, which is the voltage division at the input. But if you ignore that voltage division at the input, the gain is of the form minus Gm times R. When you discuss MOSFETs, you'll see that most of the MOSFET gain equations will be a multiplication of Gm and R out. So Gm, that is the transconductance, multiplied with the output resistance, that will give you the gain in most of those MOSFET-related problems that we'll solve later in the class. But this is just, I just wanted to mention that because then you can probably look back and kind of relate it with this understanding that you got from your homework 1. that your gain eventually will look something like GM times R, and that can be multiplied with a scaling factor depending on whatever voltage or current division is going on. Okay. Any other questions related to homework 1? If not, let's move forward. Today we are going to discuss feedback and a little bit of, if time permits, little bit of op-amps as well, which you already learned in 3111, but I just wanted to do a quick recap of the op-amps. And from next class onwards, we'll look into non-idealities of op-amps, which will be new in this course. So before going there, I wanted to quickly discuss about feedback systems and what is meant by feedback. So of course, in your op-amps in 3111, you know that there could be circuits or systems where you have an input signal coming in, you do some kind of operation on that input signal, then finally you have an output signal. Now, if you are feeding back some part of that output signal, let's say this is your VO, which is your output voltage, and VS was your input source voltage. So this is your VS is source voltage, VO is output voltage, and then you're feeding back some part of VO, maybe multiplying it with a scaling factor beta, and then that becomes your feedback voltage. Let's say you take that feedback voltage, subtract it from the input voltage VS, and that subtraction VI, which is nothing but VS minus VF. So VI is nothing but VS minus VF according to this diagram, because your input is coming in here, your feedback is coming in here, you subtract the two, that gives you your VI, which is the actual input voltage to your amplifier, which has the gain of A. And the output of the amplifier is your output signal. So that's a general structure of a feedback amplifier. Okay. Now, if you want to find out the loop gain, sometimes you'll hear about this term, loop gain, and let's try to make sure that all of us are following the same terminologies from now on. What is meant by loop gain? The loop gain in a feedback system is just a multiplication of all the gains that are present. So, for example, in the forward path here, if you look into the forward path, the gain is what? The gain is A. The amplifier has a gain of A. On the other hand, in the feedback path, you had a gain of beta. Right? That's the feedback gain, beta. Now, the loop gain is basically a multiplication of these two. That's it. Right? And how it is defined in a more technical way is that first you break the feedback loop. So if you want to find out the loop gain, you first need to break the feedback loop. So you break the feedback loop anywhere. Let's say you're breaking here. And then you want to find out whatever gain you have in the entire system. So that would be beta multiplied with A, if you look into this. So in this case, let's say you want to apply a test signal xt. So that's your test signal xt, and you traverse the entire chain. So you don't have any other, just remember how you are solving your Thevenin problems, that when you are providing any test signal, you'll not apply any other signal at the input or whatever in the circuit. So at the input, you're not providing anything at all. So you have your test signal and you traverse the network. So you have a gain of beta at first. Then you have a negative sign, which is interesting because that means your gain now becomes negative beta, minus beta. And then you have a multiplication with A. So the overall gain of this system is going to be minus A times beta. Okay. Now, if you want to find out what is the absolute value of that gain, generally we say that the absolute value of the gain is just A beta, and that's the absolute value of the loop gain that you have. Okay. So loop gain just means a multiplication of all the gains that are present in the system. And for that, you may want to break the loop anywhere that you want. And then, of course, don't apply any other signal, apply a test signal at the point where you have broken the loop and find out what is the overall gain. And that's the open loop gain or open loop gain of the system. Right? And why is it called open loop? Because now it's not closed loop anymore. You have broken the closed loop system and created it as an open loop. Right? So you have opened the loop and looking into the gain. What are the different kinds of feedback systems that we generally see in electronic circuits? So as you know that your output could be voltages or currents, your input could also be voltages or currents, right? And that gave you 4 different types of amplifiers, like our 4 different types of gain of amplifiers: voltage over voltage, current over current, voltage over current, and current over voltage, right? So 4 different possibilities. Same thing happens with feedback systems as well. It's simple. Electronic circuits are simple. You have one idea, apply it in multiple places. That's it. So when you're talking about feedbacks and different types of feedback systems, it's all about whether your input quantity is of voltage or current, and if your output quantity is of voltage or current, right? In most cases, unless you're dealing with very complex systems where your input or output is time, for example, it could be those, there could be those scenarios. But for now, let's just concentrate on voltages and currents. So you can have 4 different types of feedback systems. One, where input is voltage and the output is voltage. So you take some of that output voltage, let's say you take some of that output voltage or a part of that output voltage and feed it back at the input side. So that will be called voltage sensing and voltage mixing. And sometimes whenever you're talking about voltages, it will be represented as series, because you know that voltage sources can be connected in series. So think about your flashlight batteries, that you just put 2 of them or 3 of them in series, right, in your flashlight. And that creates a higher amount of voltage. So voltage sources can be connected in series to get a higher voltage. Current sources can be connected in parallel or in shunt to create a larger current. So whenever you see a term called series, you'll know that it's related to voltages. If you see a term related to shunt or parallel, that means you're dealing with currents. So again, this is just nomenclature, but if you think about it, this will become very intuitive at some point, that whenever we are dealing with voltages, we can add voltages up in series. You cannot add voltages in parallel, right? You do not put 2 voltage sources in parallel, because then they will fight each other. Similarly, you do not put 2 current sources in series, because then they will fight each other, right? According to KCL and KVL. So that's why you put 2 current sources in parallel always, and if you have multiple voltage sources, you'll always connect them in series. So what does voltage series feedback mean? The first term will always mean whatever you're sensing. So for example, you sense some quantity and feed it back at the input and mix it with the input quantity, right? That's what you do during a feedback. So these are again nomenclatures, but I'm trying to break it down so that you understand this better, that the first term will always mean that the quantity that you're sensing. And where do you sense the quantity? At the output, because you sense the output and feed some of that back into the input. Right? First, you need to sense the quantity before you can feed it back. So the first quantity is the sensing quantity. That always happens at the output. So your output is a voltage. If someone tells, I have a voltage sensing for a feedback, that means the output is a voltage. Now, if someone says that I have a series mixing, now series means, of course, you're dealing with voltages, and mixing is happening at the input side, because you take some of the output and mix at the input side. So series mixing or voltage mixing means that your feedback quantity is a voltage and your input is a voltage. So that's what voltage sensing, series mixing means. Similarly, voltage sensing and shunt mixing will mean your output is a voltage and feedback quantity is a current and the input is a current. So that's what we see in the diagram as well, that your input quantity was a current, your gain is voltage over current because your output quantity is a voltage. The feed forward gain is a trans impedance gain. Voltage over current is impedance. So your output is voltage, input is current. You take some of that voltage, feed it through this beta network, the feedback network. And of course, the feedback network has to convert that voltage back into a current, because your input is a current. Right? Your output is a voltage, but your input was a current. So your feed forward path has to convert current into voltage, whereas your feedback path has to convert voltage back into a current. So voltage sensing shunt mixing will mean your output is voltage and feedback quantity and input is current. Similarly, you can intuitively understand what would be the other 2 scenarios. The other 2 scenarios could be current series. So the first term, which is always related to the output, will mean, or basically the sensing term, that means that you sense some amount of current from the output. So your output is a current. And your input is a voltage, because the second term says it's series. So first term is output, the second term is input. Or the first term is the sensing quantity, the second term is the mixing quantity. So output current and input and feedback are voltages. And then finally, you can have a current shunt feedback where your output is current, your input is also current. Right? So you sense some of that output current and mix it back at the input side. So again, just voltages and currents, 4 different choices. Okay. Now this table shows what is the gain, what is the feedback quantity, and what is the gain with the feedback quantity. So gain without the feedback, so that's basically the feed forward path. So whatever gain you have in the feed forward path, that is your A. Whatever gain you have in the feedback path, that is your beta. And that's the nomenclature is same for all 4 different types of feedback. The feed forward path, the gain will be called A. The feedback path, the gain will be called beta. The overall gain of the system, which is the gain with the feedback, that overall gain of the system is going to be called A subscript F. So the gain with the feedback. So for voltage series, your gain without feedback is VO over VI, the output voltage. So if I go back 2 slides, your output voltage is VO, and your input voltage at the input of the amplifier was VI. So the amplifier just amplifies that VI voltage and produces a VO voltage. So A is VO over VI. On the other hand, beta was VF over V naught. So VF is the voltage feedback quantity that you're feeding back at the input, and VO was your output. So beta is the ratio of VF over V naught or VO. And what would be the overall gain? The overall gain is your final output over the original input. Your original input was VS, right? Your original input source was VS. So V naught over VS will give you the overall gain in presence of the feedback. Whereas A is just the gain of the amplifier, which is VO over VI, as shown in this diagram. And beta is just the gain of the feedback network, which is VF over VO. Question. VO is the output. So V subscript O is for V output. That's all. Can you put what?
VI. What is VI?
Okay. That's a good question. So VI, what is VI? So as you see that, if I go back maybe 1 or 2 more slides, so this is the same configuration that we are using in all those conditions. So your input signal is V source, the source voltage. Your output is VO, that's the final output. Your feeding back part of it, which is VF, that is V feedback. VS minus V feedback is VI, right? Because you have this subtracted here at the input, and VS minus VF is your VI. That becomes your input of the amplifier, of the feed forward amplifier. So feed forward amplifier gain is A, which means that the output VO is A times VI. Okay. And that's what kind of this table summarizes, that what is A? A is VO over VI for voltage series. For the feedback network, it's VF over VO. And for the gain of the entire network, it's VO over VS. Similarly, for other scenarios, you can just follow the table, but it's basically voltages and currents. That's it. Yes.
So on this table, it says gain without feedback is a function of VO and VI. But if you go back 1 or 2 slides, VI, I'm pretty sure is also a function of the feedback network.
Exactly. That's a great question. That's why I have more slides. This slide is not the end of the class. Okay, so, but that's a great question, that your VI is a function of VS and VF, right? VI is not an independent quantity. It is a function of your VS and VF, because VS minus VF is your VI. And that is the reason why. So before going into that actual derivation that you just talked about, keeping in mind that my VI is a function of VS and VF, I'd like to talk about 2 more things about positive and negative feedback. So what is a positive feedback and what is a negative feedback? The difference in terms of this diagram is just that for a positive feedback, you'll add the feedback signal with the input signal. And negative feedback is where you'll subtract the feedback signal from the input signal, right? So so you see that here both of them are plus, you're just adding them up. Here it's a subtracted. That's the basic difference between positive and negative feedback. Yes?
But you said VI is just VS minus VF?
For negative feedbacks. So I didn't give you the entire truth at that point because I wanted to make things simpler. But because most of the times we'll be discussing negative feedback in the course, but there is also a concept of positive feedback. So for positive feedback, VI will be equal to VS plus VF. That will be the only difference. And here, VI will be equal to VS minus VF. And then all other calculations will be very similar for both of these feedback types. Right? But positive feedback means you feedback and add to the input. Negative feedback means you feedback and subtract from the input. Question?
Positive
feedback cause like a quick saturation?
It can cause quick saturation. It can also cause oscillations. We'll see. We'll have some examples, and maybe the next slide will help you understand this better. That what does that mean? What does positive and negative feedbacks mean? So, of course, let's think about our own body, the human body. So we have multiple feedback mechanisms, and generally, like all those feedback mechanisms are negative feedback. Why negative feedback? Think about it. That let's say you have we all have body temperature regulation, right? Okay, let's take this question first, and then I'll discuss. You can do that, yes. So that would be like more detailed concepts when we discuss later. You can actually have a fractional feedback system, and then your limit could be, you're saying that the saturation limit could be defined and you can control it. That's what you're getting at, right? Yeah, it should be possible. So let's think about our body temperature regulation, right? So our body temperatures are always regulated at, let's say, around 37 degrees centigrade or 98 degrees Fahrenheit and so on. So how does it get regulated? And I know that this is hot inside the room right now and your body is trying to regulate your own temperatures, right? So, and same thing happens when it is very cold. So you have some sensors in your body. What are those sensors? Those are the nerves or the neurons in your skin, and then eventually connecting to your brain. And then your brain takes the decision whether the outside temperature is hotter than your body or cooler than your body. And depending on that, there is a temperature regulatory center in the brain. If it is too hot, the temperature regulatory center in the brain, what that will do is that it will ask the sweat glands to emit sweat, right? And so that the body cools down a little bit. So that is what happens when the body temperature exceeds 37 degrees centigrade. If it is lower than 37 degrees centigrade, you need to have enough, let's say, storage of energy producing elements in the body so that you can heat the body up and eventually again reach the 37 degrees centigrade. So if you want to stabilize something, similarly, if someone is diabetic, for example, that your blood glucose levels can increase, and at that time you'll secrete insulin from your pancreas, and then that would reduce your blood glucose levels. On the other hand, if your blood glucose level reduces, then you secrete glucagon, and then your blood glucose level again rises, right? So this is an example of a feedback system that you use or you sense some quantity, and then helps you to stabilize the entire system better, right? So you sense what is your blood glucose level, and depending on that, your autonomic system decides whether to secrete insulin or secrete glucagon, right? Similar thing happens when it is a temperature regulation system. Now, what does it mean in terms of electronic circuits? Now, again, let's say if you have increased your output voltage, let's say you increased your body temperature. So what should be the goal? Your goal should be to reduce the body temperature back to 37 degrees, right? So in that case, if you want to reduce your body temperature, so if VO increases, you want to reduce your V in, right? You want to reduce your V in, and that will only happen if you have a negative sign over here, right? Your VO increases, which means your VF increases, but you want to reduce your VI. That means you have to subtract it. Because if you reduce your VI, only then your VO will go down. So again, think about it. Your VO, your body temperature has gone up. So to reduce your body temperature, eventually you need to reduce VI, right? You have to reduce your VI. You have no control over the environment. Let's say we are stuck in this room. Whatever temperature is there in the room, we have to deal with it. We have no control over this input signal. So what does the body do? The body will secrete sweat. And you have this VF, which is the feedback from your increase in the body temperature. And you have to subtract this VF from your VS so that your VI reduces. And if your VI reduces, then your VO will reduce back to the original quantity. Same thing will happen if VO reduces first, then you need to make sure that your VI increases so that you come back to the stable situation. So your negative feedback will always stabilize the system. The job of the negative feedback is to create stable systems. On the other hand, what would positive feedback do? Your body temperature increases, You feed back some of that increased body temperature back. You add it with the environmental temperature, which is already very hot. Your VI increases even more. Your VO increases even more. And again, you feed that back and keep on increasing more and more and more. So your body temperature will go through the roof after some point. So that's why you do not have a positive feedback system in our body. You have a negative feedback system. And this negative feedback system helps to stabilize both, for example, the biological system as our body, also the electronic system as we just saw here. So if you want stability, you go for negative feedback. But positive feedbacks also have their usage. We'll see that when we learn a little bit about oscillators. So positive feedback system, what that will do is that if your input is noise, and if you can selectively feedback one particular frequency, let's say you're interested in a 1 megahertz oscillator. So if you can selectively feedback only that 1 megahertz frequency at the input and keep on adding with the noise again and again, at some point you'll see a large 1 megahertz signal just being generated from noise. That's how oscillators work. So for oscillators, you need to use positive feedback. For general electrical system where we do not want oscillation, you would be using a negative feedback. So most amplifiers work with a negative feedback system because you want to stabilize the output of the op-amp in most of the times. But if you don't want stability, you want oscillations, people generally go for positive feedback based system. Oops. All right. So let's look at the equation of negative feedback now. And we'll take a look at only one example, which is the voltage series feedback. And I guess because the other scenarios are just dealing with voltages and currents at input and output, I'm hoping that you should yourself be able to figure out what would be the equations in other scenarios. Fun fact, the equations will always be the same if it is a negative feedback. Like it doesn't matter whether you have voltages or currents at the input or output. You are dealing with the overall gain. And the overall gain, again, as you know, is just a ratio of the output quantity to input quantity. And that will remain same irrespective of what you want to have at the input or output. So let's just take an example of the voltage series feedback because that's easy. It's easy to think in terms of voltages. Your output voltage is VO. Your input to the amplifier is VI. And as you had asked this question, that VI is basically, or the gain of this amplifier A, let me use the pen. So the gain of this amplifier A is if there is no feedback, let's say if your VF is 0, if there is no feedback at all, then this part does not exist, right? If this part does not exist, there is no difference between VS and VI. Your VS is same as VI if VF does not exist or if VF is equal to 0. So if VF is equal to 0, you have no feedback. In that case, the gain of the system is VO over VS, and which is also equal to VO over VI because your VI and VS are same if you have VF equal to 0. But to make your life a little more complicated, you have VF which is not 0 right now. So if your feedback signal VF is connected in series with the input, what you can write is VI equal to VS minus VF. And remember, in this case, we are doing a negative feedback. That's why to answer your question, your VI is VS minus VF. If it were a positive feedback, it would have been VS plus VF. That's the only difference. Okay. So you have VS minus VF as your VI. Now your VO is equal to what? Is equal to A times VI. Your VO is A times VI. Because A is VO over VI, just from the definition of the gain of that op-amp. So VO is A times VI. Now, as you mentioned, that VI itself is VS minus VF. It's a function of VS and VF. So write AVI as A times VS minus VF. And further expand it as A times VS minus A times VF. Now you also know what VF is. Because beta is equal to VF over V naught or VF over VO, your VF is beta times VO. So you write that down, AVS minus A times beta times VO. Okay. Now you see you have written down your VO just as a function of VS and then a function of VO. So you can take this A times beta times VO term on the left side and write A plus A beta times VO is equal to A times VS. So the overall voltage gain with feedback is VO over VS. That's what we are interested in. So if you're interested in finding out what is my VO over VS, so the final output over the original input, that is going to be A divided by 1 plus A beta. That's the equation for negative feedback. And it will stay same irrespective of whether your quantities are voltages or currents. If you had a positive feedback, only difference is in the denominator, you'll have 1 minus A beta. Right? In the denominator, you'll have 1 minus A beta if it is a positive feedback. And if A times beta is equal to 1, 1 minus A beta will be equal to 0. Your denominator in that case could have become 0. That means that your overall gain could become infinitely large. And that's why we call that that's unstable, or that is a situation which you don't want, where things may oscillate. You'll have no control over the system. Things may be saturated, things may oscillate. And with a positive feedback, it would become 1 minus A beta. And that's why it can happen that your 1 minus A beta can be 0. On the other hand, 1 plus A beta, as you see in this particular scenario, that would be, even if let's say A beta is equal to 0, you have a 1 at the denominator, and then you have a stable amount of gain. Questions?
Corresponding terminals on the data amplifier, like they just kind of swap.
For the beta terminal, for this one you're saying? So here and here, right? Oh, okay. Right. Right, right. That's a great question, and that's a great observation. Think about it. How would you subtract two voltages? Yes. So you'll just flip those. Right? If you want to add the voltages, you have to add them in. Just think about how you put batteries in a flashlight. Right? Well, how would you connect batteries in a flashlight? So you can flip it. That will subtract the voltages. Right? And if you keep them in the same direction, it will just add the voltages up. That's all being done here. But that's a great observation. Any other question?
So if you want to find a gain,
Mm-hmm.
like the gain value for A and B, A and beta,
Right.
you need to like finding like we did in the homework, like finding the resistance value, finding the gain through the resistance value.
So you're asking that what if instead of A and beta being a black box, what if there are networks inside that, right? So yes, real networks is like that, and you'll never find a black box with a gain A. You'll never find a black box with gain B, beta in market. So you have to design circuits with it, but you can, let's say, you can model this entire, let's say, complex op amp with a gain of A, and that could become your black box. But your question is like valid because inside this black box, there could be a complex circuit. There could be an op amp, there could be multiple resistances going in and out. Same can happen with beta and so on. Right? But in a very simplest form, this is how it looks like, the equation for feedback. Right? Now, inside A, there could be 100 different circuits. Inside beta, there could again be 100 different circuits. All right. So remember that your gain, now this is an important conclusion. So your gain with feedback is A, which was your gain without feedback. So without the feedback, you only had the op amp, or you only had the feed forward path, which is this one. So you only have the feed forward path, which has a gain of A. Now with the feedback, you have divided it by 1 plus A beta. So your original gain has reduced. Right? If your gain was, let's just take an example. If your gain was 100, A was 100, here you have, let's say, 1 plus, let's say beta is 0.01. 0.01, or maybe let's say even 0.1. Let's say 1/10, that's the beta. And why I'm taking a quantity which is less than 1, I'll explain that in a minute. So you have 0.1 multiplied with 100. So you have 100 and divided by 1 plus 10. So that becomes 11. So your output is, let's say, almost, or the gain with feedback is almost equal to 10. Okay. Now, let's assume that your feed forward path is an ideal op amp. Let's just assume that for a second. So in that case, what would be the numerator? What would be the gain at the numerator if it is an ideal op amp with infinite gain? The numerator would be infinity, right? Numerator would be infinitely large. And then you have 1 plus a beta at the denominator. Now you can also represent this same this particular equation as you can divide the numerator and denominator both with a. In that case, it will look like 1 divided by 1 over a plus beta, right? So I'm just dividing the numerator and denominator both with a. Numerator divided with a, denominator also divided with a. And if your a is infinitely large, 1 over a is 0, right? If a is infinitely large, if it is an ideal op-amp, 1 over a is 0. So this 1 over a term will go away. So if you have an ideal op-amp, if you have an infinitely large gain, this equation eventually approximates to just 1 over beta. Right? So there's no effect of a at all. There's no effect of a at all if a is infinitely large. That's what it boils down to. And you can see this from here, right? So your gain was 100. So instead of 100, let's say it is 1000. So you have 1000 divided by 1 plus 0.1 times 1000. So you have 1000 divided by 101. So instead of 100 divided by 11, now you have 1000 divided by 101, which is much, much closer to 10 now. And what was 10? 10 was equal to 1 over beta, because my beta that I had assumed in the numbers was 0.1. Beta was 0.1. So 1 over beta is 10. So you're kind of converging toward a 1 over beta number as your a is larger and larger. Why is that helpful? Why is that important? Again, your a, the gain in a feed forward path, that can be implemented with, for example, an op-amp. Let's say an ideal op-amp or maybe a very high gain op-amp that you can buy from the market. Now you'll see that when you buy an op-amp from the market, if it is not a closed loop op-amp, if it is an open loop op-amp, even if they say that, let's say the gain is 1000 or the gain is 10,000, when you measure it, instead of 10,000, you might find a gain of 5,000. You might find a gain of 11,000. Someone might find a gain of 15,000. So even if they mention the gain would be around 10,000, it will move around a lot. And that movement happens because of something called manufacturing variations, that whenever you're manufacturing an op-amp or any kind of electronic system, you cannot manufacture it to an accurate degree that the value always remains constant. So instead of 10,000, the value might be 5,000 or 11,000 or 8,000 or 9,000. It could be anyone. So as a designer, and that's again, I'll be emphasizing on the design-oriented analysis, that eventually our goal is to maybe get an amplifier with a gain of 50. And you're using an op-amp with an open loop gain of 10,000 that you buy from the market, and you see that 10,000 is not really 10,000, it's maybe 9,000. But as long as it is high enough, you can create a feedback network beta, maybe with a ratio of resistors. Right? You can create a ratio of resistors in the beta network, have a gain which is less than 1 for the beta network. That's just your problem number 1, 2, and 3 in homework 1. Creating a gain which is less than 1. That's something that can be put inside beta. What's the advantage? If you create a gain which is less than 1, your 1 over beta will be more than 1. So if your beta is 1 upon 50, 1 upon beta will be 50. What's the catch? Your A, the gain in the feed forward path, has to be much, much larger than 50. As long as you ensure that, you buy an op-amp from the market which has a gain of, let's say, 5,000, and you want a gain of 50 in your system, your 1 upon beta becomes 50. Right? That becomes even if the op-amp is varying. So for example, every person can have a different gain for the op-amp. But as long as you create the same beta network, your gain will be very similar. Now, why do I say it's easy to create or easy to make sure that the beta network has a fixed gain or a stable gain? That's because when you buy a set of resistors, generally they are manufactured in the same batch. And the manufacturing variations in the same batch generally goes in the same direction. So if you're buying, let's say, 5 resistors, the values could be, let's say, 1 ohm, 10 ohm, 100 ohm, 1000 ohm, and 10,000 ohms. Generally, if you see the 1 ohm resistance has become 1.1 ohms, the 100 ohm resistance will probably become 110 ohms. And the 1 kilo ohm resistance will become 1.1 kilo. Generally, they go in the same direction if it is the same batch, because manufacturing variations are not random. They are generally because of some deterministic reason that, oh, somehow I did a higher amount of ion implantation. somehow my temperature was higher than what it should have been during the fabrication of those resistors. But it's the same for all those resistors. So in a batch, generally manufacturing variations go in the same directions. They are not really random. But when you're buying the op-amp, everyone had bought op-amp for your lab classes, right? You'll see, like when in your lab, that everyone's op-amp will behave differently because they can come from different batches. But if you're buying, let's say, 10 resistors at the same time, and they are provided to you by the manufacturer directly, those manufacturing variations will be in the same directions. What that means is that the ratio of the resistor will be same. So if your 1 kilo ohm has become 1.1 kilo ohm, and if your 1 ohm has become 1.1 ohm, the ratio of those two is still 1000. So it's easier to create a beta network that is more stable. It is easier to create that passive beta network which has a gain of less than 1, and you can make it more stable as compared to the stability that you can expect from your op-amp. And by stability here, I mean the stability of the gain from one op-amp to another. So using this negative feedback, this is one example where you are creating a more stable system that eventually you have a gain of 1 upon beta, and that is much more stable than a gain of, let's say, A in the original open loop scenario, because now you have a much better control over the gain, and 1 upon beta will be much more fixed, much more constant as compared to what you had for A. That's just one example, the manufacturing variation, that's called process. Now there could be scenarios where there are voltage fluctuations in the system. There could be temperature fluctuations in the system. And if there are these process voltage and temperature or PVT fluctuations in the system, the gain A keeps on varying significantly. You just do the temperature, the measurement outside in heat, you'll see that you'll see a very different result for your gain A. On the other hand, for your beta network, whether you do it in the lab within the air-conditioned system or if you do it outside in the heat, you'll see the beta network, your problems 1, 2, and 3 in your homework 1, they will have very similar results. So the fluctuations in a passive beta network is much lower than the fluctuations in the active network created with an active gain element A. And using a negative feedback, you can stabilize the gain. So your A over 1 upon A beta, if your A is very large, that results in, or eventually that boils down to 1 over beta, and that 1 over beta is a very stable number. That's the reason why people go for this negative feedback system. So we'll discuss more in the next lecture. I think I had 1 or 2 more slides, but I think we'll discuss that as well as ideal op-amps in the next lecture, which will lead us to the discussions of non-ideal op-amps.